Yeah, so what we should know in this section, the first part is this part, this one, is this one. Yeah. And now I will tell you the examples. Of course, you should know the examples. Of course, you should practice some examples. You will get better. You will get better. Okay. Okay. So now I could erase it. Yeah. For the graph, you should think about this graph. And of course, for the material in this chapter 11. This section 11.6, it must be the difficult one. It must be the complicated one. Yeah. But for its result, it's not difficult one. For its result, I mean, actually for its result, you just need to know this one. And they are related, so just these two parts. For topic 1. For the first topic, you should know this one. Okay, here I'll give you some examples. First one, find a gradient of fxy equals x squared y cubed subtract 4y. And the directional derivative of f is at a point P 2 negative 1 in the direction Yeah, x squared y cubed subtract 4y. Okay, let's see the first question. I will give you 3 examples. Yeah, so you practice. Okay, so first of all, gradient. So as we say in each section, actually almost in each section, first of all, you should consider partial derivative, right? When we consider gradient, it also means partial derivative. So first of all, we know that f sub x is exactly, when you consider the derivative with respect to x, then uy is constant. So x squared is derivative 2x, and the y cubed is constant. Just keep it. And subtract, it's constant. So consider its derivative, it becomes 0. So just have this 10. And f sub y. Now it becomes x. Now x is constant. Keep it. So y cubed is derivative is 3y squared. So x squared times 3y squared. Subtract 4y is derivative is 4. So it becomes 3x squared y squared subtract 4. This one. So the gradient f xy is exactly the first part. So it's 2xy cubed, 3x squared y squared subtract 4. This one. But our question is, let me see, in this point 2 negative 1, their gradient and the directional derivative. So I have not done. So it's 2 negative 1 is gradient. In this point is gradient. As we say, once I give you the function f contains 2 variables, even the function contains 3 variables, it's similar. Yeah, it will be similar. Yeah, later I will tell you. Yeah. So once I give you a function and give you 1 point, then its gradient is fixed. Just consider its partial derivative and plug in the value, then you fix the gradient vector. So here is the 2 times 2 times negative 1 cubed. 3 times 2 squared times negative 1 squared subtract 4. So here it becomes negative 1 times 4, so it's negative 4. And it's 1, so it's 3 times 4, so it's 12. 12 subtract 4, so it's 8. So it's negative 4, 8. Negative 4, 8. This one. This one. So it's the first part. And the second part, directional derivative at this point in the direction V. In the direction V. So we have a point P, 2, negative 1, and which direction? I just give you directly 2, 5. So probably it's this one, 2, 5. 2, 5 is our direction. But so now if we want to use the directional derivative, if we use this form, gradient multiplied by unit vector. So it should be unit vector. So it has the same direction, but this vector is not unit vector. So if we have vector and but it's not a unit vector, what can we do? If we want to make a unit vector and it has the same direction as V, what can we do? Just divide by its length, right? Okay, so for its length, it's equal to square root of 2 squared plus 5 squared. So square root of 4 plus 25, so it's 29. So you could see directional, the unit vector is the V divided by its length. So it becomes 2. Oh, sorry. Let me see. Yeah. Divided by its length. So here is 2, 5. Square root of 29. Square root of 29. This one. Okay, so now directional derivative at the point 2, negative 1 is exactly just gradient f 2, negative 1 and u, the inner product. So just consider the inner product. So it's negative 4. So it's negative 4 times 2 over square root of 29 plus 8 times 5 over square root of 29. So both of them have the square root of 29 in denominator, make a common denominator. Numerator, the first term is negative 8. Second term is plus 40. So it becomes 32. So it's 32 over square root of 29. 32 over square root of 29. Okay. It's the first question. It's the first problem. And I erase it for a sec, and I will tell you second problem. Did we say this section is a little complicated? Yeah. But if you just follow the formula, it's not very complicated. Just follow the formula, it's not very complicated. But you should know how to use that. Okay. Now let's see second example. We still have two examples. Second example, I should write down the problem firstly. So find a directional derivative fxyg equals sy plus yg plus ex and the point P 1, negative 1, 3 in the direction. Do you see that? Okay. For this part in the direction. It's okay. Yeah. For the direction, for the directional, find the directional derivative. Derivative of f in the direction direction to sorry, the P1 and P13 in the direction Q to Q245. So that FSYG be nature of SY, nature of YG, and nature of GX. So let me see. What's this? In that direction, oh, here. Let me see the statement. Oh, for the first statement, it's the same. The second statement, find the rate of change of F and the point P111 in the direction to Q203. Second one, in what direction? What direction does F have? The next one, rate of change. What is the misplacement? Rate of change. Of course, you could ask the minimum. Yeah. Okay, let's see. Okay. Yeah, so I will write down here, but it will be senior one. But before that, there's one thing I would like to remind you. In this example, we just consider two variables. And for the definition, I also giving you the two variable function. A function which contains two variables. But even for three variables or more variables, even at least for three variables, we also could define it by the same way. I mean, we still have directional derivative. We have a unit vector u s0 yg. So here it should be abc. We have unit vector abc. It means that its length is 1, and we still could define the u f of s0 y0. And it's defined by this way, image of point 0. Originally, its definition is similar. I mean, S0 plus H, Y0 plus BH, G0 plus CH, subtract F of S0, Y0, G0, divided by H. Yeah, the similar definition, even it has three variables, we could define it by this way. And we still have the same result, du f of s0, y0, g0, and then for the unit vector, the inner product. So we still have this result. Yeah. Okay, so now we use this result, and here I erase it. It's the first topic in this section. In this section, we have two topics. Okay, so now let's see second part. So second problem, for second one, so if we want to use this solid its gradient. So there is something known as gradient f, and it means f sub x, f sub y, f sub g. Plug in the value as 0, y0, e0. Okay, so first of all, first of all, we should consider its partial derivative. Okay, so it's partial derivative, f sub x. So now the variable x, so it could be y and the g are constant. So y, g are constant. So we just say y, this term is y, this term is 0, this term is g. So first term is, so it becomes y plus g. Probably we have seen this example before. Yeah, I mean this function before. And here is x plus g. And g, it becomes x plus y. Y plus s is the same. It's the same. Y plus s. Y plus s. Probably sometimes I just give the x, y, the notation. So the gradient f s, y, g is y plus g, s plus g, y plus s is plus. And we want to know at this point p. Okay? So at this point is 1, negative 1, 3. So it's negative 1 plus 3, so negative 1 plus 3 is 2. And the s plus g, 1 plus 3 is 4. And the y plus s, so it's negative 1 plus 1, so it's 0. So it's gradient in this one. So as we say, if I give you a function and I give you a point and I ask you the rational derivative of this function at this point, so even I have not given you any direction. For its gradient, it's fixed. For its gradient vector, if I give you a function and a point, you could decide the gradient vector. And now I give you the direction. But the direction is this one. I mean P is 1, negative 1, 3. And we have a point Q. Q is 2, 4, 5. So in the direction P, at P in the direction to Q. So in the direction to Q. So it's this one. So our direction is PQ, right? P is the initial point, Q is the terminal point. So it's 2 subtract 1, 4 subtract negative 1, 5 subtract 3. This one. It's our direction. But for this direction vector, it's not univector because we want to consider directional derivative, use this result. So it should be univector. But so what can we do? Divide by its length, right? So we consider its length. Square root of 1 square plus 5 square plus 2 square. So it becomes 1 plus 25 plus 4. So square root of 30. So square root of 30. So the univector you could just consider, just divide by its length. So the univector u is 1 over square root of 30, 5 over square root of 30, 2 over square root of 30. Just this one. Okay. Yeah, so finally, the final step, the u f of 1, negative 1, 3, gradient f, 1, negative 1, 3, u, their inner product. So just their inner product. So I could write down here. So 2 times this guy, so it's 2 over square root of 30. Plus 4 times this guy, so it's 4 times 5, 20, divided by square root of 30. And the plus 0 times this guy, 0. So finally it's 22 divided by 30, square root of 30. This one. So it's the second problem. And for third problem, for the first one, Find the rate of change. Rate of change is exactly directional derivative. Rate of change at some point in the direction, so it's exactly directional derivative. Okay, so first sub question is similar as this one, so just follow the similar way. So just consider it's partial derivative. But before that, let's see what's the function. Here, of course, you could consider its derivative directly for this function. But if you see natural log, what can we say? Natural log, if in its inside is this one, then we could separate, right? It becomes this one. Yeah, we have some property. For natural log function, we have this 10. So first one, it becomes natural log x plus natural log y. Second one, it becomes natural log y plus natural log g. And the last one is natural log g plus natural log x. Okay, so actually for this function, we could rewrite it. For this function, we could rewrite it. For this function, now it has 2/10 of natural log x, 2/10 of natural log y. Here is natural log x, here is natural log x, and here is natural log y. So 2/10 natural log y, 2/10 of natural log g. So actually f of x, y, g equals 2 natural log x plus 2 natural log y plus 2 natural log g. This one. So if you consider its gradient f x, y, g is exactly f sub x, f sub y, f sub g. Okay? Yeah. So consider its partial derivative with respect to x, then view them as constant. So their derivative is 0. And this part is just 2 times 1 over x. Since natural log x is derivative to 1 over x, so it's 2 times 1 over x, so it's 2 over x. And then here, these 2 times are 0, and its derivative is 2 over y, so it's 2 over y. And here is 2 over g. This one. But we consider the point, at this point, is directional derivative. So p is 111. So gradient f 111 is exactly 2 over 1 is 2, 2, 2. Okay. And again, at this point in the direction to q, in this point in the direction to q, so it's similar. So we consider the vector pq. We start at p and end at q. So q, the point q subtract the point p, so it becomes 2 subtract 1, 0 subtract 1, 3 subtract 1. Okay, 3 subtract 1. It's 2 subtract 1, 0 subtract 1, 3 subtract 1. Okay, but it's not univector, so we should divide by its length. So now we should divide by its length. And its length is 1 square plus negative 1 square plus 2 square. So it's equal to square root of 114, so it's 6. 6. 6. So our univector u is, we should divide by square root of 6. So 1 over square root of 6. Negative 1 over square root of 6. 2 over square root of 6. This one. This one. And the final step is directional derivative at this point 111. Exactly their gradient and the univector their inner product. So their inner product, so it's 2 over square root of 6 plus subtract plus 2 times negative 1, so it becomes subtract. Subtract 2 over square root of 6 plus 2 times 2 is 4, 4 over square root of 6. So finally it's 4 over square root of 6. 4 over square root of 6. This one. Yeah, so it's the first sub-question. And the second question is in what direction does f have the maximum rate of change? Maximum rate of change. And what's the maximum rate of change? Rate of change. Yeah, and okay, I could, yeah, so for this part, I erase just keep this one. So for second question, as we say, for the gradient vector, it's fixed. If I give you 1 point, at a point, okay, actually it means that at this point P, 1, 1, 1, at this point P. So once I give you a function, the function g equals f of sy is y, and I give you a point P1, 1, 1. For its gradient vector, it's already fixed. For its gradient vector, it's exactly just, probably just this one. Gradient f1, 1, 1. It's already fixed. It's 2, 2, 2, this vector. And now we should decide a vector, a unit vector. And if I don't have no idea, I just write down u, and it's ABC. But we know that it's unit vector, so its length is 1. Its length is 1. And it has the angles, the angle between these two vectors is theta. And for its directional derivative, here, of course, they have different. I could use another notation, u1. Okay, so the question is, in what direction does f have the maximum rate of change? So our question, the u1 f for any u1 for any u1 unit vector, for any unit vector, okay, for any unit vector. For any unit vector u1, we know that the u1 f is 0 f1, 1, 1. Okay, this point 1, 1, 1. Is equal to gradient f1, 1, 1, and the unit vector u1, their inner product. But two vectors, their inner product is exactly equal to we have the formula cosine theta equals gradient f u, the inner product, gradient f is length times u is length. So we have this formula, gradient f1, 1, 1 is length, times u1 is length, times cosine theta. We have this formula. And then here, u1 is unit vector. So for any unit vector, even I don't know it's which one, so its length is always equals to 1. It's always equals to 1. So its maxima, if we have the maxima, cosine theta should be equals 1. Right? And what does it happen? It happens in cosine theta is the function, so it happens in the case when theta equals 0 degree. If and only theta equals 0 degree. Theta equals 0 degree. Theta equals 0 degree. Okay? And what does it mean? It means that the unit vector I choose, I could just choose the vector in its gradient, okay? I could just choose the vector in its gradient. Of course, if you want to say unit vectors, you should divide by its length. Anyway, you should choose the same direction, right? And its maxima is exactly this one. Gradient f is the maxima. And in this case, it also means you could choose the vector u1 as, just consider this vector is fine. Just consider then okay, it's not unit vector, so you could choose u1 has the same direction as, u1 has the same direction, okay? u1 has same direction as its gradient. Okay. Okay, so for this problem, I write down the solution. Here I just tell you the process, but for this result, actually you could write it down in this way directly. For second one, you could write down in this way directly. So in the direction, it happens in the case, in the direction, as we say, in the direction of gradient f1, 1, 1. just this one, right? In the direction of gradient f111, and it's exactly this vector 222. F has maximum rate of change, and its value is gradient f111, its length, and it's exactly equal to its length, so it's 2 squared plus 2 squared plus 2 squared and the square root, so it's 4 plus 4 plus 4 is 12, square root of 12, so it's 2 times square root of 3, so we are done. You can just write down this part. Yeah, here is just for you to explain, just explain for you. Yeah. Okay, so it's the first topic in this section. In this section, it's the first topic.